Hi, in this video I would like to go over a sample stoichiometry problem like we will find quite often throughout the rest of the course. So we use stoichiometry in a balanced chemical equation. So we have here a balanced chemical equation of the combustion of octane. So if we have 2 octane right here, so 2C8H18 plus 25 oxygens, so that is a combustion reaction. So it's the reaction of octane, which is a component in gasoline. You might have seen the octane rating displayed on a gas pump, and that is based on the combustion of fuel. So it's a way to standardize the performance of fuel. So a higher octane rating does not necessarily mean a better fuel, but it means different ignitability properties, and those are then tailored to different types of engines. So octane is used there sort of as a pseudo reference standard. It is a component of gasoline. So C8H18, that's why the name octane has, because it's got 8 carbons in it. That's the reason for the name. And it reacts with 25 oxygens to make 16 CO2. And that's one of these things we're concerned about, the combustion of these fossil fuels, because they release large amounts of carbon dioxide into the air, plus 18 H2O. So 1 gallon of gasoline contains approximately 3,500 grams of octane, and we can actually do another calculation based on using the density, but let's leave that for another time. So the question now here is, how many kilograms of carbon dioxide are produced? Now, as we discussed in lecture and in other videos, we cannot use these stoichiometric coefficients as grams. Okay, so these are just meant to be counts. So this is being read as 2 molecules of octane react with 25 oxygen molecules to make 16 CO2 molecules and 18 H2O molecules. So these are not necessarily, or these do not represent grams. So these are actual counts, number of molecules, and by extension we can relate to the number of molecules to the number of moles. So we cannot express these as grams. So it's very important to do that. So if we say we start off with our mass of CO2, or our mass of C8H18 is 3,500 grams, and so, or 3.5 kilograms. So the question is, how many grams? So the logic here would be of so let's write the strategy out that we want to do right here. We want to have the grams of C8H18. And so the strategy would be right here that we need to do is we need to convert these grams to moles. So let's do this here to save a little room. So convert these to moles of C8H18, moles of octane. Then we can use the mole ratio in the balanced chemical equation to find the number of moles of CO2. So moles of CO2. And from there we can then go to find the moles of CO2, then use the molar mass to find the grams of CO2. Grams and kilograms. So we can find grams of CO2 and kilograms of CO2 in that extent. So for step 1 right here, we just use the molar mass. Here we use the mole ratio. And for step 3, we can then use again the molar mass of CO2. Okay, so in this case right here, we want to divide this by the molar mass of octane. So divide by 1 over the molar mass of octane, C8H18. For the second step, we just use the mole ratio, which is 2 to 1. So let's just write this out as mole ratio, multiplied by the mole ratio. And for step 3, we again need to then multiply by the molar mass to find the number of grams, multiplied by the molar mass of CO2 in this case. So let's do that in these steps right here. So we find then the number of moles of, so this would be step 1, the number of moles of C8H18 is then, if we start off with the 3,500 grams, and then we need to multiply this by something to end up with moles. And so if we take that conversion ratio right here, we want the grams to cancel out, and we have 1 mole at the top. And so that in the molar mass of this stuff is, and I looked this up earlier, is 114 grams. 114 grams. So we see the grams cancel out, and we're left with moles of C8H18. So this is grams of C8H18, and so we start off with grams of CH818 right over here. And if we do that, we end up with 30.7 moles of this stuff. Let's write this all out, that we have the proper number of moles of C8H18. And then if we go to then step 2, we need to then find out, going back here, we need to now find out how many moles of CO2 we have using the mole ratios from our reaction right here. And let's do that then. So in step 2, we would have the mole ratio, then we would have the 30.7 moles of C8H18. So let's look at the number of moles of CO2 that we want to calculate here. We're starting off with our starting quantity, which is 30.7 moles of octane, C8H18. And we know that we want at the end here, we want moles of CO2. We want moles of CO2. Write this a little bit neater. So that means we want, right here, we want the moles of C8H18 to cancel out. So we want those to cancel out, and we want moles of CO2 in the numerator. So we want that to cancel out, so then we know from the balanced chemical equation, we cannot know this without having a balanced chemical equation. So that's why it's very important to have a balanced chemical equation. And so we know it's 2 to 16. Okay, so it is 16 moles of CO2 for every 2 moles of octane. So it's basically just multiply this whole thing times 8. So 16 moles of CO2 for every 2 moles of octane. And we're left with moles of CO2. And if we do this, we end up with 246 moles of CO2. And then step 3, we want to convert this now to grams and kilograms. So let's look at the mass of CO2. And the mass of CO2 is then, we start off with the number of moles times the molar mass. So we stand up with 246 moles of CO2. And now we just need to do this, multiply this by the molar mass of CO2. Which is 44 grams per mole. So again, we want now the moles to cancel out. So in this case, we're multiplying by the molar mass. So that's very important to keep that distinction right there. So 1 mole is 44 grams of CO2. That's 44.0. Let's edit that. And if we do that, if we plug that in, we end up with 10,824 grams of CO2. 10,824 grams of CO2. And since we want this in kilograms, we end up then the mass of CO2, let's convert that to kilograms. Make this a quick calculation here at the end, is then if we have the 10,824 grams and divide this by 1,000, because there's 1,000 grams in a kilogram. 1 kilogram is 1,000 grams. So we end up with the three significant figures, 10.8 kilograms of CO2, because I only have the molar mass here reported to three significant figures, kilograms of CO2. That's a lot for 1 gallon of gas, so we end up with about 20 pounds of carbon dioxide for just 1 gallon of gas. So that's something worth considering. So anyway, so here's another example question. Let's see if you get that one right. Thanks for watching.